This video will lead you through some examples on how to add and subtract radicals. Now, as it says right here, we can add and subtract radicals just like we add and subtract polynomials from Math 10. We first have to look for like terms. So we group our like terms and we add and subtract their coefficients. Now, this will become more clear as we work through some examples. So the first example, 3x plus 5x, this is an example from grade 10. And we're looking right now, they both have variables of x, and one has 3x's, one has 5x's. So together, if we were to combine 3x's with 5x's, that would lead us to the answer that we have in total 8x's. So that's a review from grade 10. Now we move on to some of the skills here in Math 20. Here's some radicals, and we've been working on simplifying radicals. These both have simplified radicals of root 5. So what we have here are two like terms. The first term is saying I have 3 root 5s, and I want to add to it 10 more root 5s. So in total, I would have 13 root 5s. In essence, I'm just adding the coefficients on the terms that have the same radical. We could take this one step further to have a little bit longer of an expression, and we're saying let's simplify this. Let's add and subtract what we can. So if we were to examine this, we have 5 root 3 minus 2 root 2 plus 3 root 2 minus 3 root 3. So we can see we have some like radicals. The first one I'd identify is saying I have some root 3's right here. I have 5 of them. And over here, I have minus 3 root 3's. So if we read this left to right and remember from polynomials that the sign in front of a term belongs to that term, we could read this as 5 root 3 minus 3 root 3. So I have 5 of them. I'm taking 3 of them away. I'm left with 2 root 3's. And now we're done with the root 3's. And if I examine the middle two terms here, I have a negative root 2 and a positive root 2. I can combine these. I can say the first one here is negative 2 root 2's, and if I add to it 3 more root 2's, I actually have, if I remember my integers, 1 root 2, a positive root 2. Now we'd never see this written as a 1 root 2. We'd simplify that and just say final answer is 2 root 3's plus a root 2. Now let's look at the last example on this page. It's saying root 27 minus the root of 12. As it stands when we examine this, we can see that the root of 27 and the root of 12 are not like terms as they sit. So we always have to consider, like we've been doing for the last few days, can we simplify these radicals? And if we can simplify them, will they turn into like terms? So I'm going to start with the root of 27. If I look at this through perfect squares, I can see that the root of 27 is actually the product of the root of 9 times the root of 3. I choose those two factors because the root of 9 is a perfect square. The root of 9 simply equals 3, and I can drop this down with it. So the root of 27 simplifies to 3 root 3. Now I look at the root of 12, and I look for perfect squares, and I see the root of 12 is the same as the root of 4 times the root of 3, and I know the root of 4 is 2. The root of 3 can't be simplified any further, so it stays, and this was talking about a subtraction. So now the initial question, which was root of 27 minus root of 12, can be rewritten in a form like this. 3 root 3 minus 2 root 3. Now I can see that we actually do have some common radicals here, some common terms. So I have 3 root 3's, and I'm going to take away 2 of them. I'm left with 1 root 3, which, as we just discussed, would be written as the root of 3. So we can summarize this by saying to group, which kind of means adding and subtracting. So to group radicals, we must always simplify the radicals as much as possible first. So we're going to look at that in this example. We have some radicals that are simplified, some radicals that are not. Maybe they all come down to radicals that have the same radicands. Maybe they don't. So what we're going to do first, we're going to look at this. We're going to simplify all of the radicals first and then see what we can combine. So when I look at the root of 8, I can identify that the root of 8 is the root of 4 times the root of 2. We choose that because we know that the root of 4 equals 2, and this root 2 can't be simplified anymore. And if I look here at the root of 2, that just stays as the root of 2. The root of 72, now from our work, previously we know we could break this down, but we could take smaller steps or larger steps. This breaks down, if we searched our perfect square lists, to the root of 36 times the root of 2. And it might take you a few steps to get there if you chose smaller perfect squares first, but that's all right. And the root of 36 we know is 6. This can't simplify anymore, so we have 6 root 2 with a plus. And the last one, 5 root 2, there's no simplifying that can go on there, so this just continues on down to 5 root 2. So when we consider this example, we can see all of these simplified to a root 2. They don't always have to simplify to something that can be combined, but in this case it does. And we just read from left to right and we add up what we can. So when we look, I have 2 root 2's plus 1 root 2 plus 6 root 2's and plus 5 root 2's. So in total, 2 and 1 is 3, plus the 6 is 9, and plus a 5 is 14 root 2. So the initial question, root 8 plus root 2 plus root 72 plus 5 root 2 all simplifies to 14 root 2. And you can verify that by looking at the decimal approximations in your calculator. Now we're going to use these skills in a problem-solving sort of context. So right here is our situation. I have a triangle, and this triangle has 3 sides on it. You can see that I wrote that this triangle is definitely not drawn to scale. The first question I want to ask is, what is the longest side of the triangle? Of triangle ABC. So when we consider this, since it was not drawn to scale, we cannot just measure it and see what they are. Also, because we're in a class where we are learning how to do this algebraically and how to actually compare things without just looking at their decimal approximations, we're going to consider all 3 sides and try to break them down to see if there's something we can see common or longer in any of the sides. So we're going to look first at side AB. Side AB, which is right here, is 3 root 5. Side BC, which is along here, that's 6 root 125. And the long side there that looks longest along here, side AC, is 10 root 45. So again, as it stands, there's really no way I can compare these unless I looked at the decimal approximations. But we need to know how to prove this in a mathematical sense that isn't just using our calculator. So we're going to break all these down into simplest form and see if they can be compared that way. 3 root 5, we should be able to identify that we can't break that down anymore. The root of 5 cannot become any smaller. Now we're going to look at 6 root 125. 125 is a fairly large number. Maybe we can break it down. I'm going to do it again in perfect squares. And I'm going to say the root of 25, the 6 will stay, is the same thing as the root of 25 times the root of 5. I chose those two because root of 25 is a perfect square. That equals 5. There's already a 6 out there, so those two will multiply The root of 5 can't simplify anymore, so I get the root of 5 to come down, which means this guy simplifies to 30 root 5. So side BC is 30 root 5. And if I compare these two sides right now, definitely side BC is longer. I'm going to look at the last side, 10 root 45 for side AC. I'm going to solve this one with factor trees. Some of us still like using factor trees, and that's fine. So the 10 remains, but the 45 I can break up. And the 45 breaks into 5 times 9. The 9 can break up even further to 3 times 3 with a 5. There's my factor tree coming down. The 5 stays. And I'm going to have to simplify this now. Because the index on this radical is a 2, I group my prime factors into groups of 2. That's my only group of 2, those two 3's. So that group of 3's is going to come out front and be multiplied by the 10, and the only thing remaining underneath there is the 5. So now 10 times 3 is 30 with a root 5. Look here, and that's the length of side AC. So if we were to look at this question and saying, which side is the longest side of triangle ABC? Well, the longest sides are actually sides BC and side AC because they both have a length of 30 root 5. I can extend this question a little further and say, part B, what is the perimeter of triangle ABC? To do that, we should recognize that the perimeter is just asking us to add the 3 lengths on the sides of these triangles. And if I look at the triangles, I have the 3 lengths right here. So all I need to do is add up these 3 to get the perimeter. So I have a 3 root 5 plus a 30 root 5 plus another 30 root 5, which means in total, the perimeter of this triangle ABC would be 3 plus 30 plus 30, because they're all root 5s. So that gives me 63 root 5 units. So whatever we're measuring in, centimeters, meters. So as an exact length, the perimeter of these are 63 root 5 units. Now we're just going to consider one last example. I'm going to tackle this example showing both methods using factor trees as well as using perfect squares. And remember, all of these can be done with cubed roots as well. We learned how to simplify cubed roots also. So I'm going to start looking at this. Simplify 2 root 72 plus 3 root 54 minus 7 root 24. None of them have the same radicand, so we can't combine them as they sit. So we should try to simplify these. So I'm going to simplify all of these first using factor trees. So I'm going to look through all these radicals, break them down with factor trees. So this first one, the root of 72, well, that's 9 times 8. 9 breaks down into 3 times 3. 8 breaks down into 4 times 2. Then these 3's keep down. The 4 breaks up. 2 times 2. And this 2 stays. This is under a radical. We can't forget that this all had a 2 out front still. So now, because this is a square root, I look for pairs. So there's some pairs. So I'm going to have this original 2 multiplied by the 3 that comes from this pairing, multiplied by the 2 that comes from this pairing, and I'm left with a root 2 underneath. So this all turns out to be 12 root 2. So I simplified the first term. Now we're going to move over to the 54. And the 54, 9 times 6. The 9 breaks up into 3 times 3. The 6 breaks up into 2 times 3, and those are all prime numbers. So this stays under the radical. We can't forget we had the 3 there. Again, it's a square root. We look for pairs. There's only one pair. I have a pair of 3's, which means that these pairs are going to come out with this 3. So I'll have 3 times a 3. Underneath here, I just have 2 times 3. So this guy is going to simplify to 9 root 6. And it was a plus sign in the middle of them, so I can add that. Let me just put this in line with the rest. So plus 9 root 6. Then out the back, we're going to deal with this 24, which is 4 times 6. The 4 is 2 times 2. The 6 is 2 times 3. Those are all prime numbers, so that's broken up. We have this minus 7 that's still kicking around out front. It's a square root again. I look for pairs. So there's the only pair I have. So that's going to come out front with the negative 7. So I'll have negative 7 times a 2. Underneath the radical is a 2 times 3. So this simplifies to minus 14 times the root of 6. So now if I look, here's the expression with some simplified radicals. I look for some pairs of like terms, and I can identify right now that those root 6's are my like terms. So I have a positive 9 of them, minus 14 of them. So 9 minus 14 is a negative 5 root 6. We need to be very well versed in our integers. 9 minus 14 is negative 5, and the root 6 stays. There's no like terms for the root 2's, so they just stay 12 root 2. There is our simplified answer to this question. And that was done with factor trees. I'm going to do the same example now, right here, but I'm going to do it with perfect squares. And you can see that if you get well versed in your perfect squares, if you get very proficient in them, it's going to make the task a lot quicker. So I'm going to simplify the root of 72. That's 36 times 2, and I still have this 2 out front. Square root of 36, that's 6, times the 2 out front, and a root 2. That gives me 12 root 2. I move over now to the 54. The 3's out front. 54 is, put the perfect square first, root of 9 times the root of 6. The root of 9 is 3 times the root of 6. So now 3 times 3, that's 9. Root 6. Move over to the 24. I have a minus 7. Looking for perfect squares. Minus 24 breaks up into root 4 and root 6. The square root of 4 is 2. There was already a negative 7 there with a root of 6. So this simplifies into negative 14 root 6. And you can see, without the factor trees, I got to the same spot as the last question. And I need to group my like terms again. A positive 9 and a negative 14 gives me the negative 5 root 6, with the 12 root 2 having no like term with it. And we've reached the same solution, or the same simplified expression, using, I'll put it up here, using perfect squares. Now really, it doesn't matter what you use. If you use your trees, you're going to need to really organize your work well, because you'll have a lot more stuff on your paper. If you're using perfect squares, great. The important thing is you pick a strategy, either the perfect squares or the factor trees. You pick a strategy that works for you, get really good at it, and that's going to ensure that you have a good understanding of this.